Good morning, I'm Michele Zanoni, a researcher from RSC, Italy, and today my presentation deals with automated tool based on deep learning to assess voltage dips validity, integration in the QuEEN medium voltage network monitoring system. The outline of the presentation is the following. So we start from framework and open issue in monitoring system in distribution grid. Then we present a deep learning algorithm, the DELFI application. It is a tool for validity assessment of voltage dips, and we integrate this tool in our monitoring system thanks to the QuEEN PyService application. Finally, we perform some power quality analysis on voltage dips, and we go to conclusion. It is well known that nowadays the widespread diffusion of renewable energy sources distorting loads drives the interest in power quality. So in the new challenges of the smart grid scenario, power quality is a key task, especially in medium voltage distribution grid. The parameters and the quantities to be monitored can be found in the standard EN 50160. In particular, we focus our attention today on voltage dips. What is a voltage dips is a temporary reduction of the voltage supply. And voltage dips are characterized by origin and validity. They are two fundamental characteristics that we have to consider if we want to talk about voltage dips in a regulatory purpose. In order to properly characterize these events, advanced signal processing technique and machine learning algorithm can be optimal toolbox. RSC developed since 2006 a power quality monitoring system in the Italian medium voltage distribution network. We have installed nearby 400 measurement units in the primary substation connected to the low voltage side of voltage transformers. These instruments are able to perform power quality measurement according to the standard IC 61430. And additionally, they are able to acquire waveforms and RMS sequences during special events as voltage dips. Statistics and results of our monitoring system can be found on our website. In the Italian distribution grid, we have a certain number of isolated neutral systems. In this kind of topology, it is well known that faults involving ground produce a sinusoidal zero sequence that can cause voltage transformer core saturation, producing and resulting in a false voltage dips. So, as we can see from the picture in the slide, we have a reduction of the voltage at the output of the transformer, characterized by distorted waveform. And this reduction is not a reduction of the voltage supply, but it's only the results of the saturation of the voltage transformer. If you want to consider voltage dips as a parameter to evaluate the power quality of our network, these events has to be removed from statistics. So at the beginning of the QuEEN monitoring system, an algorithm, a criterion, has been installed in the measurement unit. This algorithm is based on the second harmonic component measurement. So for each line-to-line voltages, we measure the second harmonic. And when the value of the second harmonic exceeds a threshold for a minimum number of consecutive period, this event has been recognized as false voltage dips. But we have experienced that there is a certain number of not defined cases in which the criterion is not able to give an answer that are not considered. So we have nearby the 12% of annual events that are classified as not defined and so are not considered in the analysis of voltage dips. So in order to overcome this problem and to increase the capability of our monitoring system, we developed in the last year a new criterion based on deep learning that is called DELFI. That is deep learning for false voltage dips identification. This deep learning algorithm takes as input data the RMS voltage value as an image, and it performs a classification that gives us always a Boolean answer. So we have true, false, or some special event that are true plus false. So we train this deep learning algorithm, and preliminary results in terms of accuracy are very good, because we achieved an accuracy of 95%, but of course on a small set of events equal to 130. And naturally, this algorithm for now is not implemented in QuEEN system. So our goal today is to integrate, to test this new algorithm in a new scenario, considering a bigger set of events. So in order to achieve this purpose, we built a tool called QuEEN PyService in Python language that it is able to integrate our database, our QuEEN database, with advanced functionality and services. So this application directly speak with our database. That is basically MySQL database, and it is able to read all the voltage dips recorded by our measurement units, to read the QuEEN criterion based on the second harmonic, and to generate the image of the RMS voltage recorded. Moreover, that is the key task, of course, they integrate our DELFI application in our QuEEN database system. So we can compare the results of this new algorithm, of this new deep learning algorithm for false event identification in the real system, in our database. So thanks to this application, we perform some broad statistical analysis. We consider voltage dips recorded by 61 measurement units from 2015 to 2020. So we analyzed nearby 43,000 of voltage dips. That is a big amount of events, of course. Okay, in this analysis, we have removed events occurred simultaneously with the tripping of high voltage line, distant protection, because these events has to be attributed to the transmission system operator, because they are high voltage origin events. So what kind of analysis we perform? First of all, we compare basically the results, the classification results of the QuEEN criterion based on the second component with respect to the new criterion based on deep learning. Then, once we have the two classifier results, we perform some power quality index as N2A and N3B with respect to the equivalent measurement point. So N2A is the number of voltage dips that occur below the immunity zone for class 2 equipment, while N3B is the number of voltage dips occurs below the immunity zone for class 3 equipment. The first analysis, we have the results of the QuEEN criterion, the classification results of the QuEEN criterion, and we can see that we have a trend for each year that tell us that there are 78% of true events, we have the 12% of false events, but we have considerably 11% of not defined events that are not considered in the statistics. If we move to the deep learning approach with the DELFI application, we can see that the number of true events are increased because we have an 85%, while the false events remain basically the same, from 12% to 13%. the true plus false events are negligible as they are equal to 1.8%. So first conclusion, we can say that a certain number of not defined events are now classified with the DELFI classifier as true events. But these events can contribute to the power quality because then we evaluate the N2A and the N3B for both the criteria. So we have that if we consider the QuEEN criterion, we have an average value of the N2A of 32 plus 2. While if we consider the DELFI classifier, this number are equally to 40. The same as for the N3B average value. We move from 14 plus 0.8 for the QuEEN criterion to 20.6 for the DELFI classifier. So second conclusion, we can say that the not defined events by the QuEEN criterion are now classified as true. And so we have to consider in the statistics of our power quality analysis. These events contribute to both N2A and N3B, so are not negligible events. Going to conclusion, we can today we present our QuEEN PyService application, that is a tool that integrates advanced functionalities in our monitoring system, that is the QuEEN system. This has allowed us to test and verify a deep learning algorithm, the DELFI classifier for voltage diffs validity. And we tested on a very large amount of data, nearby 4,000 events. And the comparison between these two criteria tell us that not defined events by the QuEEN criterion are most classified as true by the CLIS classifier. And those events are not negligible as they contribute to boost N2A and N3B. Thank you for the attention, and I'm here for questions.